All right, here we go for real this time. Is it clear how this first column, ignore the other columns right now. We're just talking about this column. It's not A and not B. We get that. Not A and not B. That's that whole column, okay? Do I have that example? Okay, I don't. And this is what it would look like. This is when I'm using those little circle shorthand. I could also draw it with actual NAND gate, or like NOT gates, pardon me. But if I want the second column, well, that's not A and B, right? Think about that. Not A, that's 1, and B. Well, that'd be a 1 and a 0. That's 0. 1 and 1, that's a 1. Hey, there we go. And then 0, 0, and 0, 1 is 0. Did somebody? 7 minutes.
Oh, sorry.
No, you're not. Get in here. Close the door behind you. So the next column is this. In fact, whenever you want like a force a pattern, when you want to force a very specific pattern, we can make use of AND gates. So I'm going to jump down to here. This is where we finished last time, right? This will only be true. This will only, because remember, AND, typically, with AND, only one combination of inputs will ever give you like a true. Every other combination gives you 0. So ANDs are really great for when you want a very specific pattern. Here, the pattern would be 0, 1, 0, 1, 0, 0, 1, 1. If that was the input pattern, we output a 1. Otherwise, it's a 0. So we're leveraging this fact. And that's what we're doing here. I want to see a 0, 0, I output this. If I see a 0, 1, I output that. If I see a 1, 0, I output that one. If I see a 1, 1, I output that one. If I see anyone's combination on any other gate, it won't produce anything. I mean, here with 2 inputs, I can only have 4 possible combinations, and one of these 4 gates, only one will ever be active at a time because we've generated all permutations or combinations, whatever. Clear? So that's what's going on here. And remember, this was that decoder. That was that thing where like, oh, I'm controlling my sprinklers, right? With 2 buttons, I can control a total of 4. This design scales forever. We could make a 3-bit decoder really easily, following the same general pattern. Any questions about the decoder? Okay, in general, AND gates with various inverted inputs are ideal for situations where a very specific input pattern is required. And this is where we were going. We talked about the decoder symbol. It's that, what did we conclude? It was a rhombus? Trapezoid? Fine, okay. It's a trapezoid. This is the symbol, right? This part specifically. It's a 2-bit, meaning it would have a possible 4 outputs. But we noticed that there's only one input line. Remember we talked about this at the end of last time? But we can do that with this splitter merger thing, where you can effectively combine multiple signals on a single line. It's going to become very important once you start, having bigger and bigger circuits. Yeah?
Do you have to have 4 outputs?
You don't. I don't know. Digital might get mad if it's not connected to something. Let's find out. Let's just find out for fun. Oh, this has been running all day. What am I doing? logic. Okay, there's those. Okay, great. And then maybe I don't actually have a circuit for that. So here, we'll just do a new one. Let's build it. And because we might be doing a bunch of this today, I'm just going to do what I did yesterday and steal this mouse. Of course, I don't have enough USB ports. Oh my goodness. All right, I guess I'm not stealing this mouse. Shoot. Components. Under plexers, we have a decoder. Let's make it a 2-bit. So with 2, we can have a maximum of 4, but let's find out if digital requires us to have 4. In principle, we don't need 4. We just need a, we can have at most 4, right? But the question is, does digital require us to have 4 connections? And maybe it does. Let's find out. If it does, there is a way to make it, not complain. We can actually do this, by the way. And then remove data bits, yeah. So we don't need the splitter. I can actually set this input to be multiple bits. So I say, and then I can be like, okay, I want it to be 2. Okay, yeah, all right, and then 3, cool. So let's see what happens if we don't have one. It's still happy there, but what happens there? Yeah, it's fine. Okay, I guess in digital we could ignore 1. If it wouldn't let us ignore, there is like, you could connect it to ground. You can connect it to this like not connected component to mean like, yes, shut up, that type of thing. Yeah. For the sake of making it match what we had, let's use again, a splitter and a merger. It looks like by default it wants to merge 2 4-bit lines into an 8-bit line. We want 2 1-bits into a 2-bit. And input. I'm going to make it a small shape. So 0, 1, 2. Whoop. Oh, and well, we can put that back. There. It should be clear that although with the 2 bits, like it should be clear that order matters, right? 0, 1 gives us this, and 1, 0 gives us this. It could be the case where you can mirror this. Whoop, oh shoot. Right? And then suddenly you're like, okay, 0, 1. You're like, what? That's not 1. Well, yeah, because I've changed the order of the bits. Be mindful of the order of the bits. Here, this is the 0 bit. This is the first bit, and so on and so on and so on. So just be mindful of that. That can get you. In fact, be mindful of like, okay, we have A and B, right? And notice that like in this example, this would actually be the 0th bit, and this would be the 1 bit. We read it right to left. Be aware of that. I mean, am I really? I mean, that's just by convention, right? It doesn't have to be, but be aware of what bit's what. Okay? Questions or anything? Concerns, comments? Okay. This, though, like, this is what we built. This and this the same thing. Okay? This is an example of a combinational logic where there's no the output depends entirely on the input of this and no other state or anything. And because this design pattern is so frequent, we generalize it with this symbol. The point is, whenever you see this symbol, like that right there, really what I have is that AND gate configuration. Okay? But this is an abstraction. So we already now have another layer of abstraction, right? Transistors to gates, to fancier gates, to things like this. We're moving quickly. A lot of abstraction as we go. This one symbol means that series of AND gates. And this is just showing you the splitter merger. Here's the merger, here's the splitter. And it's all the same component in digital. It all just depends on how you configure how many inputs, how many outputs. Cool? Now, multiplexers, often called muxes, multiplexers. They are used, they're going to feel similar to a decoder, because they are, but they have a different utility. Multiplexers are used to select one of many input signals. So a decoder basically took we can think of it as literally it took a binary number and selected that number's signal line. Okay? Okay? Yeah? So it took some input and it turned one of these lines on. A multiplexer is a little different. It selects one of many input signals to map to an output. So imagine I have a bunch of input signals and I have one output and I need to select, okay, which of these signals am I going to send on the line? Okay? Imagine I'm an old-timey operator and someone wants to make a phone call, right? I've got a billion phone lines and I want to connect these two. Well, which of these, who's calling who? Okay, I take that signal and connect it. They were being the multiplexer. So the input signal could be arbitrary, high or low. They only have a single input. And in addition to input signals, multiplexers have a selector signal to control which input it's mapped to. The below truth table demonstrates the desired functionality. Okay. This is where I have a 1-bit selector. I have two input signals, okay? A and B. All right? I have one output, but I also have this select. So you can look at this and be like, so really there's 3 inputs? Yeah, but let's make sure we know how we separate them, in our heads. 2 input signals, okay? This is the selector, and this is what the output signal is going to be. So really, what I have here is, in fact, do I have a simplified version? I do, yes. Let's go through this, and then we're going to talk about the simplified version. A 0 is 0. Both inputs are nothing, and I'm selecting 0. 0 is going to be one of these 2 inputs, okay? Let's see if we can find out here. Okay, so I guess 0 selects this column. Okay? The quietness, I can never tell. Are you quiet because it makes perfect sense, or are you quiet because it makes no sense at all? It's just a truth table. The answer to my question, are you quiet because it makes sense and quiet because it makes no sense, was this is really what I mean, okay? I don't care if it's a 0 or a 1. I don't care if it's a 0 or a 1. I just have some input signal. If I select 0, I take the X. If I have 1, I select the other one. That's the idea of a multiplexer. And we want this idea to be generalizable. What if we had 2 selector bits and 4 inputs? Well, yeah, with 2 selector bits, I can specify which of the 4 signals to pass on to the output. If I had 3 and 8, and so on and so on and so on. So yeah, here the values of x and y are not important. What is important is that the value of whatever it is, x or y, 0 or 1, is mapped to the output based on the value of the signal. I think, so like these 2 truth tables are communicating the same idea, but not only is this one smaller, I think it's also clearer, right? The intention of what is it doing is a little bit more clear. This one, I think it's easier to get lost in the zeros and ones. You know, forest through the trees, so to speak. Below is an image of a 2-bit multiplexer. So we use it with AND gates. Right? So we use the AND gates kind of as, in a similar way to the decoder. Now, it might not be obvious, because this is only a 1-bit selector. 2 inputs, right? But in general, if we would have every combination in the same way that we had the decoder. Okay? Every combination, I think it's going to be easier if we jump to this one. Okay? So this is the same idea, but it's a 4-bit multiplexer. It has two input bits, 2 selector bits. Okay? Consider that this pattern, the top 2 input signals, okay, on every one, based on my design, because I have the actual like signals. Let me be clear with my words. These are the signals I want to select from, the inputs. The way I configured it, I always have the input being the bottom signal to the AND gate. But 2-bit selectors, the top 2, it's the exact same pattern we're following with the decoder. 0, 0, 0, or 0, 0, 1, 0, 0, 1, 1, 1. But there's a 3rd input. Well, yeah, the 3rd input, it's a 2-bit selector. That means we have 1 more input, which is the actual signal that I might want to pass on. If this is, let's imagine we had 0, 0. That means this AND gate is like ready to turn on. If this is a 0, we get 0. If this is a 1, we get 1. This won't be activated, this won't be activated, this won't be activated, because this is like active. These 2 signals are like ready to go. So it's like, okay, I've got everything I need to output a 1. So if you give me a 1, I output a 1, assuming like this is the input signal. If you give me a 1, I output a 1. If you don't, well, I just output 0. The selectors like get the AND gates ready to go, and then whatever the signal is, the actual input signal, will get relayed. Like, if you can think of it like that. So this is basically a decoder with a fancy extra feature where it relays some input signal, at least at this stage. But what's going on here? Well, we'll talk about that in one moment. Do we have any questions about this? Yes?
So what is the advantage of this over like the decoder?
Well, the decoder, this could be a 0 or a 1. This could be a 0. I know this almost looks like, isn't that just basically like a 3-bit decoder? But it's not. Because if it was a 3-bit decoder, there'd be like 8 signals that I could select between. This only has 1 output signal. What's up with that? And really, it's what's the function? Based on this, let me try to come up with an analog. It really is like, consider that this might be going like Like 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, right? Don't think of it as like a static signal. Think of it as like a signal is coming through. Like maybe someone's talking and like there's a signal line, okay? These say which one do I want to go to the output. If I select 0, 0, okay, that one, this signal gets out to here and just gets relayed out. So that's kind of the idea. Where the selector, it's like, well, which of the 4 things do I want to water? Which of the 4 things am I going to set to high? This is, which of the 4 things am I going to map the input signal to one output? Yeah?
This isn't exactly like a technical sort of like application thing, but you can sort of say it's basically you're asking a kid which flavor of ice cream do they want if we're for a decoder versus only this kid gets ice cream. Do you want ice cream, yes or no?
I'm trying to think. So the first one is like, which of these 4 ice creams do you want?
Yeah, basically, and they choose. So like obviously whatever input they get, the output is the ice cream they want, right? Versus you have a bunch of kids, but you're only choosing one kid to get ice cream. But if they don't want ice cream,
They get to pick which.
Well, no, they just decide. But if they don't want ice cream, then no one gets ice cream.
Yeah, okay, I see what you mean. Why did you think of that example of all things? But yeah, okay, if that helps you, great. It is weird, because they do seem very similar, and they are very similar. But this one is, one of these is always high. No matter what, one of these is going to be high, based on what that input is. Here, there's no guarantee what output is going to be. There's only one output. There's no guarantee what it's going to be. But I can tell you where its output came from based on the selector. Happy, sad questions? Ask the questions now. Now, you might be wondering what's going on here. Why do we have an OR gate? First of all, the OR gate's purpose isn't so much right now. This OR gate isn't so much about doing an OR. We know that at any time, at most, one of these signals is 1, right? They might all be 0. If I select this input signal, it could be a 1 or a 0. If I select this input signal via the selector bits, right? If this is the signal that's selected, this output is 0, this output is 0, this output is 0, no matter what, right? By nature of how these AND gates work. If I select this gate, this signal to go through this gate must be 0, this gate must be 0, this gate must be 0. Regardless of what these are, these must be outputting 0. Why must they be outputting 0? Because if this one's selected, that means the input was 0, 0. 0, 1, that's false. 1, 0, or sorry, 0, hold on, 0, 0. 0, 1 is false. 1, 0 is false. And 1, 1 0, 0 is false. Did that help or did I just make it more confusing? Because I said it wrong in the end and I flipped it. 0, 0. This is like ready to be activated depending on this signal. 0, not 0 is 1. What's 0 and 1? 0. And then I don't care, right? It's already false. 0, not 1, not 0, 1, and 0. So 1 and 0 is false. And I don't care what that is because it's already set to output false. And 0, 0, what's 0 and 0? 0. And anything, I don't care, it's 0. You look, I don't know how convinced you are.
Well, to me, then why are there 4 inputs? Like, if only the first one matters.
Because right now, and then I'm like, oh, now someone else is calling that wants to connect to the line. So, okay, end your call. Now you get to talk to them. That's really it. These are all going like zeros and one. I could have several of these in a row. Like there's a lot of things this could be doing. The whole purpose of this is it's mapping some input to an output. One of several possible inputs to one output line. And we select which of the inputs gets mapped. That's all it's doing.
So using the selectors, you have to put input there too.
Yes, but the function of these is different. These selector bits will pick which of these inputs value will be relayed. The input value could be a 0 and it could be a 1. Or it could be like 0, 1, 1, 0, 1, 0, 0, 0, 1. Like think of it over time, right? And then like, okay, that signal's done, time to change it to this input. Okay, now this value is getting mapped to the output. And then I go, okay, now I want 0, 1s, and then so on and so on and so on. So back to what we were going. If the input is 0, 0, this gate is set to 1, 1, and whatever this is. But I know this is already going to be false, false, false. This might be a 0. It might be a 1. If it's a 0, what is 0 or 0 or 0 or 0? 0. What is 1 or 0 or 0 or 0? 1. And that would follow for all other combinations. The OR is just effectively what it's doing is this. Okay, we've got our AND gates, 0, 0, 0, nothing, nothing, 0, and then nothing, nothing. What I really want to do is this, right? Okay? Maybe I should draw it better. There. That's really what I want to do. Only one of them is going to be high. So if this is 0, 0, 0, and this is a 1, well then this is like, this line's really 1. And whatever value was inputted here, oh, I guess there should be like a third line here, right? Right, these are the inputs and the selectors, whatever. We following? So really if it's a 1, whatever, this outputs 1. If it's a 0, it outputs 0. I don't really care what these are. If you try to do this in digital, it won't work for a very good reason. You might be saying, yeah, but there's no signal on these lines. And if this one has the signal, okay, then there's a signal on the line. If it doesn't, then it's not. But whatever it is, it's whatever this value is that's relayed. So just combine the wires. But that won't work. Does anyone have any idea why it won't work?
Short circuit?
It will create a short circuit, but can you be more specific? It sounds like you might actually have, and you're like nodding too. It all comes down to the fact that a 0 is not nothing. Remember how on that AND gate we saw that weird grayed out wire? How there was like a bright green, a dark green, and in the middle there was like a gray wire. What's that? Well, 0 means this is actually connected to ground. Not always. It depends on the design of the circuit. It's whether they have like a common collector or not. It's a whole thing. But a 0 usually means this wire is connected to ground, this wire is connected to ground, this wire is connected to ground. And if I output something here, think of it, that's actually, if I output a 1, that means I'm connecting it to high. And then I'm connecting high directly to ground. So whatever signal is coming from here actually it just gets sunk right to ground, and then whatever this is, it's never going to happen. It's connected to ground. These output gates, their output is actually from like, it's tying something to ground or not. Really? So this would create an issue. We would effectively be like, well, this gate says, okay, connect my output to high. Okay, great, we output a signal, and then, well, this one was connected to ground, this one's connected to ground. So this signal immediately gets sunk straight to ground. Okay? Again, I can't tell. I wish I could, like, you should see your faces right now. You're like, Does that mean it makes sense to you? I don't know. So it's connecting it straight to ground effectively. And you can't do that. That ain't going to work. So the trick is to do that, is to use OR. Because an OR will do exactly that. It allows us to connect inputs together and to pretend it's like, oh, connecting it all to one wire. So an OR in this case solves that problem. Cool? Cool. Realistically, I mean, with digital, it's done like several things to kind of like ignore some of the real physical constraints. So there is an argument to like, well, why did they implement the AND gate such that they have like they are actually connected? Don't worry about it. I don't know why, but it was designed in such a way where that property is happening. There might be a very good reason, I'm not sure. Long story short, using an OR, that's a great way to connect several signals together without causing a short circuit. Raise your hand if you saw that coming when I started explaining why it was going to be a problem. That's impressive. Wow, well done. Good for you. If you were like, no, news to me, that's what I expected. I didn't expect anyone to kind of see where the issue would come from. But yeah, remember, 0 is meaning it's actually a sunk signal. There's a difference between, okay, you have a wire. You connect it to a charge, or you connect it to 0, to ground, or you do nothing. And doing nothing is not the same as connecting it to ground. Connecting it to ground is not the same as doing nothing, right? So it's like, well, I'm not doing anything. The output is 0. You connected the output to ground. You are doing something. Other questions about the decoder. This right here is the explanation of why can't we do that? Well, because, yeah. Yes?
So what controls the selector? How do you change what it's selecting?
No, that would be, imagine this is connected to, I'm trying to think of a real world example. I'm trying to connect it to ice cream. Why can't I think of it? It's 9 in the morning. I can't think of an example. But I'm sure there's a billion examples that could be come up with. I just can't think of it right now. Imagine these are connected to people trying to make a phone call. Okay? They've got their phone, and the signal is in their phone line. Okay? So ignore these inputs. These inputs are really there to show like, oh, whatever the signal is. Okay? I'm the operator. Okay? And there's only so many lines to connect my town. It's 1940, and there's one line connecting New Glasgow and Antigonish. I don't know, right? And so-and-so's bribed me, so I'm going to connect their call, right? But they all want to like, hey, I want to talk to whatever. Well, who am I actually going to connect to that line? So me as the operator goes like, okay, I want Bob to be able to call New Glasgow right now. So I connect, I say, okay, I want that to be, Bob would be 1, 0. So I go 1, 0. Now Bob's input, now Bob's phone is connected to New Glasgow. That's the idea. Where these inputs come from and where these inputs come from don't really matter, but it's that these inputs are doing the selecting, and this input is the signal that I want to select. Yeah?
So could you think of it like a tuning dial on a radio? Selected radio station and
Yeah. That's a great way to think of it. I mean, in that case, it's more analog in the sense that like, well, okay, well, my selector isn't, but yeah, let's draw it to like an analog comparison, right? My selector is like a dial, and I'm tuning into a specific frequency. Technically, I don't know how they break up the bands of the frequencies, right? But every radio station has like a band, a frequency band they can go to. And each of those frequency bands would be the input signal. This is my speaker. Okay? And then me, via the little dial, can specify which one. I don't know what the bands are, but I know in my car it used to always go like by 0.2, right? So, yeah, by 0.2, however many units of hertz. Yeah. Yeah. Does anyone in here not use an analog radio? No, you all have? Okay, good. All right. All right, cool. Anyways, yeah, that's an interesting comparison, especially because it's not digital to analog. Digital means like everything's been made discrete. Here I can select 4 things, right? Why? Well, because there's 4 combinations of these 2 things. Analog meaning like, well, we're now dealing in like a continuous space. We're like, what frequency is it? 102.5? Or was it 102.51 that I hit? 102.05. Like, what did I really hit, right? You know, we could play that game forever. Anyways. Analog means it's like analogous to reality where you've got like a continuous thing. Digital means it's been like, you know, discretized in a nice way. We like digital things. It's nicer and easier for us to wrap our head around. Even though it can be lossy, right? Like floating point precision, right? You can't really get those numbers. Anyways, that was a fun comparison. Yeah, that was a good one. Other questions about this? Cool. And here's the multiplexer signal, or symbol. Again, multiplexers are relatively common. So here is a 2-bit selector for a 4-signal multiplexer. Okay? This would be like the same implementation as this. 2 selector bits, 4 input signals. 4 input signals, 2 selector bits. And you're like, it's another one of those shapes? Yes, but look at the direction is different. That's it. And if you're like, that's going to be confusing, yeah. Especially because there's a demultiplexer, which is the same direction as the other one, but you would have to, what I mean is, notice the shape of the multiplexer. It's like this, right? And the demultiplexer, which, by the way, does the inverse operation of a multiplexer. Take one input signal and then select which of the output signals to map to. Okay? And if you're like, wait, isn't that just a decoder? No, because the decoder was one of these is always high, where this just relays whatever the signal is. Okay? Yeah. But you'll notice that the demultiplexer signal is like the opposite. It's like that. And then you're going to say, well, hold on. The decoder symbol was that. You're right. But a decoder doesn't have an input signal. So, you know, you just kind of, you figure it out, right? Right? If you're like, oh, crap, don't worry. It's really not that bad. You'll figure it out. What would the like what would a demultiplexer look like though? I wonder. I don't think it's too bad. Any ideas what the demultiplexer would look like? It's actually simpler than this, I think.
Would it be
That's what it would be, but basically, connect all of these to the one input signal and get rid of this part. That's it. Because remember, the OR only serves to combine the signals. We don't need an OR to split the signals. We could just branch, just like this. We could branch signals out. We're fine. But basically, pretend this is one input all connected. That's the input signal. And then we're selecting which of the four, cut this part off. So we have 4 outputs. We select which of the 4 are we going to map this to. That's how it would be. And yeah, the multiplexer signal. Demux is another common tool. It's the inverse of a multiplexer. And here's a multiplexer to a demultiplexer, right? Pretty cool, right? So this would be like the people in New Glasgow getting the phone call, and they're like, well, who am I mapping the call to on my end? And here's, okay, yeah, there we go, cool. This would be like the truth table for the demultiplexer. And you're like, hey, that looks a lot like a decoder. Yeah, it's just, again, we relay whatever this is. It might be a 0 and it might be a 1. That's why its design is effectively like a decoder. Cool. I wanted to do an activity today, but I don't think we really have time. That would be mean. Yeah. Any questions about anything so far before we get to the last thing? So a programmable logic array is with a programmable logic array, we could implement any Boolean function we want. You can draw any truth table you want that's valid. You could draw any truth table you want of inputs and outputs and make it with a programmable logic array by following a very simple, tedious, but simple pattern. So yeah, they're a very general purpose design for implementing any Boolean logic function. It can map any input to any desired output. You draw a however many output truth table. You put in whatever 0s and 1s you want. You can make it with a programmable logic array. And they're called programmable logic arrays because first of all, when we're programming it, we're not programming it with code. We're programming it like we are designing it. We can make it however we want. It's programmable. Logic because we're doing logic. An array because we have an array of these gates that we follow this simple pattern with. So these are you can do anything with this, but they get large. You can follow a pattern, and it's always going to work, but they grow really large. And with this comes a bit of a problem. You can do anything you want, but there might be a better way to create the functionality you want. And a programmable logic array is going to take a lot more gates, and it's going to be a lot more complex than maybe an alternative implementation. So there's always a bit of an engineering trade-off. But we'll pick up here on, today's Thursday, tomorrow's Friday. We lecture tomorrow. Yeah, tomorrow. Cool. Any last questions? All right.